All right, just checking the in order to serviceability check. So I'm gonna plot out the deflection diagram. Again, displays and flow chart. I'm gonna choose the wind service wind. And then instead of looking at the wind blowing X, because that's a strong axis, we don't have any significant deflection. It's pretty small. But by changing to wind blowing in Y direction, this example show me that 16.65 deflection at the top. This is my example. Yours should have a different output, right? So here, okay, there are two ways to plot out this, how to get this output. So let me just give you the practical, I'm recording it. So either, right, this is output ETABS show this. Last week we talked about how to plot out data and create the charts in Excel, right? The reason why is we're gonna continuously iterate and with a few other model. So this graphic is showing graphically, but I cannot use it. So most likely I'm gonna use this Excel format like this. I can copy and dump it here. So this is maximum, okay, this is wind Y deflections. Now you need to practice how to use the Excel. I strongly recommend or must scale. Everyone must scale Excel. Excel or something data manipulation tool is a must scale. I want you to now use it because that's industry always looking for the skill. So this is one, okay, wind Y deflections, okay. So where is my chart? So chart, okay, chart. Unfortunately, this is kind of default, it's not give me the right. So X is wind deflection in X axis, Y is floor. So I need to adjust this. This is first model, model 1. Let's say, yeah. All right. So this is my deflection diagram. First model. Okay. And yes, always data level access. Okay, legends. Okay, turn on that. So this is actually the one we completed yesterday, last week, right? So okay, this is the first model, and okay, and here we added our criteria. I'm gonna edit our I'm gonna add our criteria as well. For overall displacement. So this is, I'm gonna say 500. So, oh, okay, right. So 500. So I think upper portion we still has an issue, the deflection criteria. Let me change the chart type with the line. All right. Right. This example, I have guidelines is H over 500, but my deflection curve here is exceeded. So this one still is not good. We need to stiffen up a little bit. Now, which area better? Next case, stiffen up is more efficient because 24 inches, 22 inches, 20 inches, right? So what thickness I'm choosing it. So do we want to continuously increase the wall thickness or now adopt a new feature, Outrigger, right? So this is part of the now engineering the judgment, what system is more cost effective? Continuously increase the wall at the moment or play with outrigger? Typically, outrigger is more efficient because a wall, when you thicken up, you apply entire wall, right? So it's a material. Also, if you add more concrete, your dead load continuously increase substantially. So I think here I'm gonna stop. I'm gonna show you next step. If your team have the deflection issue at certain points, right? We're gonna now move on to next approach by adding the outriggers. All right. So going back to my model here. So I'm gonna save as the difference. This one V2. Well, let's already have V2. So now it's the beauty of tall buildings. Actually, now we are dealing with here. For example, this. Let me show you the plan. Okay, and 3D, I'm gonna turn on all column as well. So by looking at it, as I said, we have two choices. Okay, can we continuously increase the wall thickness and concrete strength? Or let's think about not considering outriggers, because we have upper portion deflection is a little bit exceeded. So if we add a couple of stiffness, maybe outrigger might be more efficient. So now looking at this, right? We have all the column. Oh, why? Yeah, let me turn on the column here. Right? So you see that small column? So now where could be the good candidate location of outrigger truss? Because the wall is pretty line up, column, wall, right? So we can add a truss here. Here. Do we need 4? Do we need 2? It depends on, but obviously all architectural program layout and structurally, I'll consider 4 location. Or obviously size 4 means your outrigger truss has a decent amount of sections we're gonna end up with. But if you're using 2, obviously much heavy section we need to end up with, right? 4 versus 2. So here, I'm gonna add a truss first on this line and this line, more symmetrical way, right? So that avoid any torsion. So my case, your case is maybe different, but by looking at mine, I have a grid line B and E. I'm gonna choose and add the outrigger truss. B, I'm gonna choose elevation B. Okay, this is my elevation. See the B? So, okay, I'm gonna randomly choose the middle height. Thing is, section properties, I need to look at it, which section property I'm gonna use. Maybe auto selection, or for now, for example purpose, I'm gonna choose W. Yeah, let me see. What is available? Okay. All right, 426. I just choose one severe significant sections, and moment release is a pin connections, right? So Control D, okay. So Control D, okay. I'm gonna place the outriggers at maybe between 18 and 20. So here to there, double story. I have to turn on the raise. Okay. Click and click. Right? So this is a diagonal. I choose one is 18 to 20 double story truss with outrigger. So this wall and column is tied together with this truss. Right? Okay. What are you talking about truss? Yeah, truss is triangular shape, some pattern of structural elements. Gonna give us the some the stiffness and strength. So tying together means this column and this, you could think of this is column and this may be deep beam as well, but we're using the deep truss. So now, in order to make this column is contributed, this should be significant member. This and this is currently your column size was actually designed by gravity load alone, right? Because current model, you didn't have any outrigger, which means your column size is based upon your gravity load alone. But now when we tie together these columns, it's going to taking lateral wind load too. We will show you. So in order to make the outrigger system works, you need to increase the significant section size here, and this truss is going to be very heavy section. So that obviously you are most likely using a big skip hole with your strong arms. Basically, you are adding the lateral stiffness. So here, right? So I'm gonna choose here a diagonal bracing and this bottom core, and then column below here, column below, I select. So what I just choose a much big section, heavy section for this. So just for make it simpler, but I think we have to optimize all these sizes. I'm just choosing W 14 by 500. Maybe not. Okay. So let me see. Maybe 14 by 500 might be not enough. I'm gonna pull it out heavier than that. So I'm gonna bring it out W 14 by 730 or something like that, or bigger. So okay, I'm gonna bring heavier sections. So column below, I'm gonna reassign W 14 by 70 here and there, and keep for now truss as 14 by 500, right? So for now, here I assign 14 by 500, this diagonal and bottom core, and this one 14 by 730. Since I did only one on the one grid line, I'm gonna do the same thing, grid line E. So I'm gonna choose grid line E. Okay. Okay, I'm gonna draw bracing by using 14 by 500, 18 to 20, 18 to 20. And select the column below, assign 14 by 730. All right, so now let me show you the 3D. All right, here. On the grid line B and grid line E, I added this diagonal Outrigger truss bracing. Let me change to section property. All right, right? So this is Outrigger truss. And the column below, I think I choose the severe section now. So let's see how much the deflection improve with this. So I'm gonna run the model. but obviously this is a simple just summary of the each run. First is a displacement. Second one is industry drift. So just in case, let me just put out the previous model, industry drift. So that is 40-story tower. Let me 40-story. Without outrigger, the first model doesn't have an outrigger, so this is the model. I'm gonna put out displacement and choose wind, service wind, and wind direction 2. So instead of displacement, I'm gonna put out diaphragm drift. So this is the first model. I'm gonna copy this and dump here. Okay. And I'm gonna add this first model ratio there. Oh, I have to add this. Okay, so this is summary of a two model. Just again, right now, basically I show you two model. One with our just wall that has a wall thickness 24 inches, 22 inches, 20 inches with various concrete strengths 9, 8, 7. Right, second model, we add the Outrigger truss. So this is a two model comparison. One is overall drift. Overall drift. See that difference, right? This is basically we increase the stiffness. So cantilever stiffness. So you see that overall drift. So overall drift comparison. Now this one is industry drift ratio between two adjacent floor. So this is our criteria. Whatever, just two floor industry drift, right? Ratio should not more than this, our guideline, H over the 350, L over 350. 350 is the uniqueness ratio. So the first model, you see that? Relatively severe, right? Once we add the outrigger, those numbers actually all push to the left. So it shows that proper meet our criteria. So basically, this is an example. I mean, the system we limited to the current the core wall, couple shear wall with outrigger. The reason why I just want you to play with, I think it's 90%. I think it's the wall, all the high-rise building, they adapting this system, outrigger system, with a concrete shear wall system. And some unique program, some project, sometimes they adapt to new, but this is more common, and that's why I want you to kind of adapt this. So far, any question? Yeah.
Yeah. So for the drift, you said it's the height over 350.
Yeah.
So
On the wall, okay. Criteria is H over 50. 1 divided by 350 is uniqueness ratio.
Okay.
So this is a diaphragm story drift. I will show you. The ETAPS give you this output, so you're checking here, basically here, diaphragm drift, right? Wind, service wind. We're talking about all service wind, but you choose diaphragm wind. But step 2 is the wind is blowing in y direction. So 2 is a wind. So because my model here, because that is more weak axis, that's why I just focus on only wind blowing in y direction, because that's a minor direction, which actually, right? So, I mean, this is a procedure. A couple of times you iterate it. Again, when you're ready, one thing that I'm gonna show you, another feature. All right, so this is Outrigger model because we already. I'm gonna turn up this extrusion. All right, so let's take a look at the actual force. Wind is blowing left and right, right? Will be interest. Look at the because we've been look at this many times. This time, yeah, wind x ultimate actual force. Okay. All right. Oh, I didn't assign the peer. All right. Let me assign the peer. So this one's assigned the peer one. Okay. This is peer 2. All right. So let me rerun it. So what I'm going to show you is the same thing that the load pass. Last week we talked about load pass among each system. Since we adapting Outrigger concrete core wall, shear wall, couple shear wall with Outrigger, we need to understand overall load pass under the wind load. Yeah, pretty much like this, right? While this one running, let me just see. So basically, we adopting either this type of system. So under the wind loading, right? Concrete core wall or just brace frames taking majority of shear and overturning moment. But when the floor, hit at this Outrigger truss, load is redistributed here. So overturning moments, right? Overturning moments, the wind blowing is pushing this cantilever. All up to here is more likely just one single moment diagram you can think of. But when we hit this, there's two components. Since we have a Outrigger column and Outrigger truss, and also still continue the backbone of the shear wall or brace frame, loading is redistributed between a couple of this one coupling forces between Outrigger column to column and within this brace frame. So you're gonna see this same force distribution in current model. Let's see. All right. So this model, let's check the actual force. But this is a wind blowing too. All right. Here we go. Right. So wind is pushing this direction. This case, you can see this. Yellow is tension, uplift. Red is compression. Wind is blowing this direction, pushing it. So overturning effect somehow come to here. We've been seeing this. Okay, there is a coupling effect, but also have a moment component here. I will show you moment component. But when this overturning moment reach out to this, we have this two system and contributed to resist overturning moment effect. So this actually coupling forces and also internal small coupling effect. So you see that two component. Now here, when you turn on the moment, you'll see also moment distributions. A little complex because this is okay. So as we here, this is actually a hybrid because we have a couple of components. Let me just open the another model. Okay. the upper portions